Welcome friends, Igor is here, and in this video we will figure out how to check if a linear system has any solutions. In this lesson we will define what it means for a linear system to be consistent or inconsistent, and we will derive a simple consistency test. Let's get started. A linear system is called consistent if it has at least one solution. A linear system is inconsistent if it has no solutions. Here's an example. The first linear system is a consistent linear system because we can produce one solution of this linear system. Now, at this point we don't know if this is the only solution of this system, but as long as we can produce at least one solution, the system is consistent. In the second example, we have an inconsistent system because it has no solutions. Do you see why this system has no solutions? Think geometrically. The two equations represent parallel lines. They have no points in common. Let's figure out a simple way to recognize consistent linear system versus inconsistent linear systems. Suppose that A is the augmented matrix of a linear system and B is the reduced row echelon form of this augmented matrix. Then the linear system is inconsistent if and only if the last column of B is a pivot column. Before we proceed with the proof, let's spell out what it is that we need to prove. The phrase if and only if in the statement of the theorem has a special meaning. It means that two statements are equivalent. The two statements we have are the linear system is inconsistent, one statement, and the last column of B is the pivot column, second statement. In order to prove that these two statements are equivalent, we need to prove that each statement implies the other. Effectively, when you see an if and only if statement in the theorem, it means you're lucky to stumble upon buy one get one free deal. This is because there are actually two separate statements for us to prove in this theorem. One, if the system is inconsistent, then the last column of B is a pivot column. And then second, conversely, if the last column of B is a pivot column, then the system is inconsistent. Please keep in mind that these two are separate statements, and one does not automatically imply another. Let me give you a simple common sense example which shows that you cannot automatically reverse an implication. Let's take two statements. Statement 1, I take my umbrella. Statement 2, it is going to rain. One implication says, if it rains, then I take my umbrella. In the opposite direction, the statement is, if I take my umbrella, then it will rain. Now I hope I convinced you that you do indeed need to prove each implication separately because they are not related to each other. Let's start our proof with the implication in the reverse direction. We are going to assume that the last column of the reduced row echelon form B is a pivot column, and then we need to prove that this forces the linear system to be inconsistent. So we have this reduced row echelon form of the augmented matrix B, and it has, let's say, R non-zero rows. I claim that if the last column of B is a pivot column, then the leading one of row R must be located in that column. Here's why. If we have R non-zero rows, it means we have R leading ones, and the leading one of row R is the last leading one in the reduced row echelon form matrix. But we also know, as we go down the rows of the reduced row echelon form, the leading ones must be located further to the right. This means the last leading one must be located in the rightmost pivot column. But if the last column of B is a pivot column, it is the rightmost pivot column, and therefore the leading one in the last non-zero row must be located in the last column of the matrix B. Now, because the leading one of row R of B is located in the last column, the previous column must include zeros, because leading one is the first non-zero entry in its row. But this row corresponds to the equation 0 equals 1, which obviously has no solutions. Now, at least one equation in the linear system has no solutions, and that means the whole linear system has no solutions. Therefore, the linear system is inconsistent, and this is exactly what we are trying to prove. In the forward direction, we are going to assume that the linear system is inconsistent, and then we must show that this forces the last column of B to be a pivot column. We will prove this fact by using the technique of proof by contradiction. Let me explain what this technique entails. We are trying to prove an implication. A statement P implies a statement Q. In our particular setting, the statement P is that the linear system is inconsistent, and the statement Q is the statement that the last column of B is a pivot column. We want to prove that if P is true, then Q is true. And the essence of the proof by contradiction method is to show that if P is true, then Q cannot possibly be false. If Q cannot be false, then it must be true. To realize this approach, we are going to assume that our initial assumption P is still true, but we're also going to assume that the desired conclusion Q is false. And then we will show that this leads to contradiction, some kind of nonsense. Let's implement this technique. We are going to assume that the linear system is inconsistent, and yet the last column of B is not a pivot column. If the last column of B is not a pivot column, it means all leading ones are located in the columns that correspond to the variables. Remember, in the augmented matrix, the last column corresponds to the vector of constants, but all the previous columns correspond to variables. But if all leading ones correspond to variables, then we can actually construct an explicit solution to this linear system. We solve each equation for the variable that corresponds to the leading one in that equation and set all free variables to, let's say, 0. This produces one solution to our system of linear equations. Therefore, this system must be consistent. But this is a contradiction, because on the one hand, we assumed that the linear system is inconsistent, yet we also derived that this same system must be consistent. A linear system cannot be both consistent and inconsistent. So what was the cause of this contradiction? This contradiction was caused by our assumption that the last column of B is not a pivot column. Therefore, this cannot possibly be true. And the only conclusion we have is that the last column of B must be the pivot column. And now we have proved if a linear system is inconsistent, then the last column of the reduced row echelon form of its augmented matrix is a pivot column. This concludes the proof of the theorem because we established both implications. The if and only if statements are very powerful because they work in both directions. So we proved that a linear system is inconsistent if and only if the last column of the reduced row echelon form is a pivot column. And so it means, therefore, that a linear system is consistent if and only if the last column of the reduced row echelon form is not a pivot column. This gives us a simple consistency test. We look at the last column of the reduced row echelon form of the augmented matrix of the linear system. If the last column contains a leading one, then the system is inconsistent. If the last column does not contain a leading one, then the system is consistent. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will prove that every linear system has no solutions, one solution, or infinitely many solutions. I will see you later.